Think about the computer sitting on your desk. In an idealized model, this single, isolated machine operates with mathematical precision. It takes the specific input, executes a deterministic process, and produces a predictable output. If a loose connector or a bad memory chip interrupts that precision, the hardware protects itself by stopping entirely. You get a kernel panic, a blue screen, and the computation halts to prevent bad data. But once we move away from that single machine and connect thousands of independent computers over a network, we lose that mathematical perfection. We enter the physical reality of a distributed, shared nothing architecture. In this environment, we encounter a new problem called partial failure. A request sent across the network might succeed, it might drop, or it might get delayed indefinitely, making the system's overall behavior non-deterministic. Unlike your desktop PC, a distributed network cannot simply halt when one piece of RAM fails. It has to keep routing traffic and serving requests while a piece of its own infrastructure is actively broken. Because the probability of a hardware glitch or a dropped packet in a massive cluster can never be reduced to zero, modern systems abandon the idea of preventing faults. Instead, they are engineered to tolerate them. To keep a service online, we have to architect for three variables: surviving physical hardware death, neutralizing spreading software errors, and adapting to extreme user load. By accepting that our physical components will inevitably fail, we stop trying to build indestructible machines. That acceptance is the mathematical prerequisite for maintaining system uptime. To build that uptime, we first have to separate a fault from a failure. A fault means one single component, like a hard drive, has deviated from its specification. A failure means the entire system has stopped serving the user. 50 years ago, preventing failures meant buying massive, vertically scaled mainframe machines designed for high availability within a single chassis. Today's data centers rely on thousands of smaller, commodity servers linked together. In these clusters, hardware faults are constant, but they are typically random and uncorrelated. One dead power supply doesn't cause a different server's CPU to catch fire. This chart visualizes mean time to failure for hard disks. In a cluster of 10,000 identical nodes, at least one drive dies every day. The mitigation is redundancy. When that failure occurs, the active data pathway seamlessly reroutes to an adjacent node. The physical server is dead, but the user never sees an error screen because the software layer is explicitly programmed to mask that physical death from the rest of the network. Once you have that redundancy logic in place, the most effective way to verify it works is to induce faults on purpose. This is the logic behind tools like Netflix's Chaos Monkey. By writing scripts that deliberately kill random processes, engineers verify that the recovery logic is active and functional. Frequent simulation verifies that the automated recovery logic works as intended, reducing the need for manual intervention when components fail during off hours. True hardware fault tolerance shifts the engineering burden away from buying indestructible machines toward writing resilient software orchestration. But hardware faults are relatively easy to isolate. Software errors are much more dangerous because they are systematic. A bug in your code is correlated across the entire cluster, capable of striking thousands of nodes at the same moment. These bugs often lie dormant. They wait until a specific, unexpected assumption about the operating environment is broken. In 2012, a bug in the Linux kernel rewriting the calculation of a leap second caused thousands of application servers across the internet to hang simultaneously, entirely bypassing their hardware redundancy. When a systematic bug like this triggers, it can lead to a cascading failure. A cascade starts small. A single runaway process eats up its node's CPU allocation, forcing connected neighbors to work harder. Those infected nodes drop offline, forcing remaining active nodes to absorb a massive influx of traffic, overloading them in a chain reaction. Stopping this requires strict process isolation. The system must recognize a runaway process and allow it to crash and restart cleanly before it can drain the cluster's shared resources. To do this, reliable systems constantly measure their own internal behavior, looking for mathematical discrepancies that indicate a silent software fault. For example, this snippet of backend code tracks a message queue. It continuously compares the number of incoming requests to the number of outgoing responses. If those two numbers diverge, the software flags a discrepancy. By detecting that discrepancy early, the orchestration layer can automatically quarantine the infected node, cutting it off from the shared network before the bug triggers a broader outage. While hardware fails in isolation, software bugs can spread across every node, requiring algorithmic quarantine to prevent a complete service outage. Even if you isolate software bugs and route around dead hardware, a healthy system will still degrade if the user traffic pushes past its capacity. Scalability is defined by specific load parameters. A server designed to handle 100,000 tiny 1 kilobyte requests per second requires a different architecture than a server handling 3 massive 2 gigabyte file uploads per minute, even though their total data throughput is identical. To see how complex load parameters dictate architecture, we can look at Twitter. At its peak scaling phase, Twitter handled roughly 12,000 new tweets written per second, compared to 300,000 timeline reads per second. Processing 12,000 text strings a second is manageable. The true bottleneck is fan-out load. This diagram shows 2 users. On the left, a standard user pushes data to 10 followers. On the right, a celebrity node pushes out to millions. If Twitter used a traditional relational database, they would optimize for the write. The system stores the tweet once. But look at the math when millions of followers refresh their timelines simultaneously. The database is strained by the massive inward pull of simultaneous read requests. They pivot to approach 2, a caching strategy. Instead of waiting for a read, the system does the work on the write. When a celebrity posts, they trigger millions of instantaneous cache writes, forcibly injecting data outward into follower nodes, straining the system differently. By defining these load parameters, the read volume of standard users and the write volume of celebrities, Twitter architects built a hybrid solution, caching the standard users and fetching the celebrities separately. Architecture must be built around assumptions of which operations will be common and which will be rare. If you don't calculate the specific math of your traffic, like the fan-out ratio, adding more servers is a waste of capital. It simply introduces new hardware into the cluster, adding new vectors for system failure. This brings us to the link between how a system scales and how reliable it remains under pressure. As you add nodes to handle heavy load, the math of the network dictates that the probability of simultaneous hardware deaths and software faults increases. No human engineer can manually route traffic around this level of physical chaos in real time. To manage distributed complexity, we rely on abstraction, hiding the chaotic physical layer beneath clean, predictable software APIs. Treating faults as routine occurrences rather than exceptional disasters transforms how we design systems. By mapping precise load parameters and isolating faults, we decouple the success of our software from the physical reliability of the hardware it runs on. The objective of distributed architecture is to build systems that maintain availability by automatically surviving the